Yes, now we see.
Okay. So as we said, we will introduce today the kinematics of a particle, which will relate velocity, position, and acceleration of particle, uh, in addition also to the variable of time, but without considering the forces acting on the particle. And in a next chapter, we will relate forces to acceleration through the law of Newton. So for today, we will define uh, position, displacement, velocity, and acceleration. We will study particle motion in case of straight line, so it's a rectilinear motion, or in case of moving along a curve, this is curvilinear motion. Also, as application, we will see projectile motion that you are familiar with. And finally, we will see analysis of dependent motion of two particles. So to begin with, already we worked on statics. The statics part deals with bodies that are either at rest or moves with constant velocity. So the main equations in statics were sum of forces equal to zero and sum of moments equal to zero. In dynamics, this is not the case. Okay. So in dynamics, first sum of forces is equal to ma. So we have acceleration. Dynamics deals with accelerated bodies, so sum of forces equals to ma. Okay, and also sum of moments equal to inertia times alpha. But we will just work on particles in dynamics. We will not work on rigid bodies. Okay, so because the rigid body is much more complex, and for the program we don't have time. So, then dynamics, as we said, will be mainly divided into two parts. The first part is tackled in this chapter, which is the geometric aspects of motion that will be used to relate velocity, position, acceleration, and time, while kinetics will deal with the relation between forces and acceleration, and we will do this in next chapter. Now, in rectilinear kinematics, we will learn how to define position, displacement, velocity, and acceleration at any instant in time when moving along a rectilinear or straight line. So this is the easiest type of motion. We start by, in order to define position, we need to have a certain coordinate axis. So here, for example, as you can see, you have you need an origin. Since it's a rectilinear motion, you just need one coordinate to define it. And of course, you select a positive direction. So, for example, here the positive is to the right of O and the negative is to the left of O. So, if you have a point P moving in this direction, then its velocity is positive. If it is moving in the opposite direction, then its velocity is negative. Now, what is displacement? The displacement of a point is the variation in its position. So delta S represents between two position 1 and 2. Delta S is S2 minus S1. Now, concerning velocity, we have several definitions for velocity. We have the average velocity, we have the instantaneous velocity. The average velocity is simply delta S over delta T. So if you move from one point to the other and we ask you what is the average velocity, just take S2 minus S1 over delta T. Now, even if you do this, so maybe you do this and you go back, delta S is the same. So if delta T is the same, then the average velocity will be the same. But of course, the average speed will not be the same. So we'll see in next slide what is difference between average velocity and average speed. So the average velocity will not take into consideration the path of motion. It will just take into consideration the displacement during the time. So if you, for example, if you start from a point, you go and then you go back to the same point, the average is zero, but you did motion. This is why the average is not always a good representation. It is a good representation in general when I have straight motion and I don't change direction. If I change direction during motion, the average speed will give me a better view of what is happening. Okay? Now, if delta t tends to 0, when delta t tends to 0, I will obtain the instantaneous velocity. The instantaneous velocity is given by a limit when delta t tends to 0 of delta s over delta t. So it's the derivative of s with respect to time. Now, the velocity is an algebraic value. It can be positive, it can be negative. As we said, if we are moving towards the right in this case, then it's positive. If we are moving towards the left, then it is negative. Now, concerning the average speed, as we said, will take into consideration the total path of motion. So if I move in this way from point 1, then I turned back to go to point 2. So this is point 1, this is point 2. If I want to calculate the average speed, I should consider the whole distance moved. So it is this distance, d1, plus this one, d2. Then I get the total distance moved. So the average speed is the total distance moved over delta t. And of course, it will be larger than or equal to the average velocity. In case I am not changing direction, okay, and I'm moving in positive direction, then they will be equal. In case I'm not changing direction and I'm moving in negative direction, then the average speed will be minus the average, because the average speed is always positive. So this is a positive number since I'm dividing a distance by time, and distance is positive. So average speed is never negative. It's always positive. However, the average velocity can be positive, can be negative, depending on the direction of motion. If I'm going to the right or to the left, or it will depend on the sense, if you want, of motion. So if I have a negative sense of motion, and I'm not changing sense with time, then if you want, v speed will be equal to minus v average. Or we can say that v speed equal to the average speed equal to the absolute value of v average. But whenever I have change in sense during motion, then automatically the average speed will be higher than the average velocity, because then the total distance will be larger than the absolute value of the displacement. Okay? Any question on this?
Here, can you please re-explain why V average is minus delta S over delta T? Where the minus come from?
Yes, here they did it in this way because they considered that delta S is just the absolute value, okay? But to be more accurate, and here they considered this is delta S. The distance is delta S, considering that this value, if you want, is positive. But it's not, يعني here in the slide, it is confusing if you want. هي إذا بدك it's minus in this case average velocity. هون كأنه أخذوا delta S positive. يعني اعتبروا لأنه حطوا لك arrow in this way, okay? So they counted that I have delta S in this way, I counted positive in this way. مش هناك حطوا minus. But since already S is selected as positive in this way, to not confuse you, لازم يكتبوا delta S over delta T. بس هي delta S تكون negative, okay? So هن just حطوها minus لأنه اعتبروا عم ياخذوا الابسوليوت فاليو، لأنه حطوا إنه delta S حطوا لها الارrow in this way. Okay, but to not be confusing, and to always follow the positive direction of S. يعني لازم يحطوها هي delta S over delta T، بس هي delta S هي negative. Okay, it is more accurate. Okay.
Yeah, okay, thank you.
هي delta S over delta T، بس delta S will be negative in this. Okay. مين كان عم يسألني السؤال؟ It's what's your name?
Yes, Michael Doctor.
Okay, Michael. Okay. So now, concerning acceleration of a particle, the acceleration will be also defined as average and instantaneous. The acceleration represents the variation of velocity with respect to time. The average acceleration is given by delta v over delta t, while the instantaneous acceleration is given by the derivative of velocity with respect to time. Okay, so we can say that a is dv by dt, first derivative of velocity, or second derivative of position. Okay, so now also in addition to these two relations, we can develop a third one that is that we can demonstrate by eliminating time. So we know that a is defined as dv by dt, and also at the same time, velocity is the derivative of position with respect to time. So v equals to ds over dt. Okay. So if you want to eliminate time between these two relations, you can, for example, from v equal ds over dt, you can replace dt by v over ds. So dt is v over ds. And then if I replace dt by its value in the equation here, if I replace dt here, I will get that a is v dv over ds. Okay, so this is another equation that I can use when I don't have to include time. It's a relation independent of time. So taking ds to the other side, I will get a ds equals to v dv. And you will see, depending on the problem, how we can, which relation to select. Okay. Now, when we say that we have acceleration and when we say that we have deceleration, who knows? When we
When the
say that we have,
velocity is increasing, we have acceleration.
okay, yani if
Or
I
when it's
want,
decreasing,
yes, it's
deceleration.
right. When it's increasing in magnitude, okay? مش in,
Yes, doctor,
Yes.
do you mean هلا in direction?
yes, I mean V can be
Yeah.
negative, and if V is negative, if I have
I
acceleration, how
don't
will
know
V?
if you mean إنه إذا particle is going up, generally the acceleration is negative. If it's going down because of the weight, it's gonna become positive.
No, I mean if I want to put a condition on the A and V, what is a sign condition? Okay, if V is negative, to have acceleration, A should be positive or negative?
Negative.
Negative. What I want to tell you is that many of you think that acceleration means a positive. No, it's not the case. To have accelerating motion, I should have same sign for V and A, because if I'm moving in the negative
Okay.
direction, I can accelerate in the negative direction. So if I accelerate in the negative direction, okay, A will be negative also. So a general rule will be that here we are talking about rectilinear motion. So A and P will be collinear. But to be general, because we will see also different cases, the rule is A scalar product of velocity is positive. A dot V is positive. So in rectilinear motion, this means that A and V should have the same sign, or both are positive, or both are negative. And of course, in case velocity is constant, then the acceleration will be zero. Okay. Now, we will derive together some typical relations that you know, which apply for constant acceleration. So, if in case we have velocity is constant, then acceleration is zero. This is the first rule. Then, if acceleration is constant, let us derive together the rule you are used to do. So first, acceleration is dv by dt. So if I want to find v function of time, I should integrate this relation. So I can do separation of variables, dv equals to a dt. When I mean separation of variables, so here I have two variables, velocity and time, and a is a constant. So when I take dt to the other side, I obtain from one side the variable v, and from the other side the variable time. So now I can integrate both sides. The first side I will integrate it with respect to variable v, so from v0 at the initial state to any time, velocity v at any time. And from other side, I will integrate from t equals 0 to t equals t. Please pay attention, not always from t equals 0. It depends on the boundary condition they gave you in the problem. Okay? So sometimes they tell you at t equal 1, for example, velocity equal to 3. So here you will not integrate from 0, you will integrate using the boundary condition given. So then here you will replace, here I will integrating from 1, and here I will integrate from 3. Okay? In general, in the majority of cases it is 0, but not always, so please pay attention for this. So if we want to have a general rule, you can put that v equal to v0 plus ac times t minus t0. T0 is, if you want, the instant at which you know the velocity. So if you know, for example, here at t equal 1, v equals 3, then t0 will be 1 and v0 will be 6. Okay. So if t0 is 0, then your equation will be v equal v0 plus a times t. And this is the formula you are familiar with. This is the formula of velocity for constant acceleration. And please pay attention for constant acceleration. A lot of students make the confusion. I gave them a problem with variable acceleration and they use this equation. You can never use this equation if a is not constant. If you have a variable, you go back to integration, you put the function a here and you integrate based on the function given. Okay? So please don't do this error. Pay attention. Now, if you want to derive a relation between velocity, acceleration, and position, independent of time, then we will use the relation that will not contain time, which is v dv equal ads. So here also we are deriving the values, the relations for constant acceleration. So here already variable are, already you have separation of variable. From this side the variable is velocity. From this side the variable is position. So now you can integrate. You integrate for v from v0 to v and for s from s0 to s. Then you will get integral of v is v square over 2. You apply it between the 2 points, so you will get this integration will give you v square minus v0 square over 2. And from the other side, the integration will give you a constant times delta s minus s0. So now if you rearrange your terms, you take 2 to the other side and you take v0 square to the other side, you will get that v square equals to v0 square plus 2a constant times delta s. Okay? I think that you know these relations from school, yeah?
Yes.
Okay. Now, finally, to get the relation between position, velocity, time, and acceleration, then I can do the rule that v equal to ds by dt, because always you will try to use the relation that will involve the variables needed. Here, you want position function of time. To get position of function of time, you should use the relation containing s and t, which is v equals to ds by dt. And already we calculated v function of time. Okay, so I replaced v by its function of time to not introduce a new variable. So now my variables will be s and t. So now I take dt to the other side to do separation of variables. And then I integrate both sides for ds from s0 to s and for t from t0 to t. So here in particular they consider t0 equal to 0. In case it's not, the equation will be as follow: s equals to s0 plus v0 instead of t delta t, yani t minus t0. Okay, and plus have at square also, instead of t will have delta t. This is the only difference. Okay, So now it's a simple integration. You have v0 plus ac times t. Then you have to replace. You should integrate this function. It's v0t plus half at squared, and then you replace your boundaries t and 0 in the relation. So you end up with s equals s0 plus v0t plus half at squared. Any question until here? Okay. Now, we will do some examples to practice on how we use these relations. So first, we have a car moving in a straight line such that for a short time, its velocity is defined by v equals to 0.90 square plus 0.6t in meter per second, where t is in seconds. Determine its position and acceleration when t becomes equal to 3 seconds, knowing that at t equals 0, s equals 0. So first, I have v as function of time. So v is given function of t. And I want to get position. So the relation I should use will involve v, s, and t. So the relation is v equals to ds over d. Okay. And since v is already given function of time, all I have to do is to replace this function here. Okay. Then all I have to find s, I should integrate. Okay. And I have my boundary condition at t equals 0, s equals to 0. So let us see together the details. So first, as a first step, I write v equals to ds over dt equals to my function. I do separation of variables. I take dt to this side. Then I integrate. For the first side, I integrate from my boundary condition. I know that for s equals 0, t equals 0. So I integrate s from 0 to s, and I will integrate t from 0 to t. Then I will find a general relation, okay, s at any time. Then I can replace, if you want, you can directly put here integral between 0 and 3. You will directly get the value of s at 3 seconds. But in general, I advise you to find the function because sometimes you will need it in other steps. Here in this problem, just you will need it here, so it's fine. You can directly integrate from 0 to 3. Okay? Now, the function here, I integrate this function, 0.90 squares, the integral is 0.3t cubed, and for 0.6t, it is 0.3t squared. Then I replace boundary conditions between 0 and t, and I will get my result. Okay, so now I have s as a function of time. I replace t by 3 seconds to get the value of my position. Okay, for integration, just you should know basic integration, and I will not give you very complex integrals. So just the main concepts of integration. Now, the next step is to determine acceleration. If I want to determine acceleration, I should go back to the definition of acceleration. A is dv by dt, so it's the derivative of velocity with respect to time. So when I derive the velocity function, which is given, directly function of time, I can get A. The derivative of 0.90 square is 2 times 0.90, so it's 1.8t, plus the derivative of 0.6t is 0.6. So now I replace t by 3 seconds to get the value of acceleration. And of course, in this problem, I cannot use the relation developed for constant acceleration because a is variable. It's function of time. Another problem, a small projectile is forced downward into a fluid medium with an initial velocity of 60 meters per second. Due to the resistance of the fluid, the projectile experiences a deceleration equals to A equal to minus 0.4 v cubed, where v is in meter per second. Determine the projectile's velocity and position 4 seconds after it is fired. So in this problem, we gave us a function of v, okay? And we want to find the projectile velocity first, then position. First, since we need to find v, and already we have a function of v, then we should think about the relation involving these two variables, okay? Which is, and of course, we want to find after 4 seconds, so also we need to involve time. So it's very clear that we should use the formula a equals dv by dt. And now, since we have a function of v, we replace a by its function. So when you replace a by minus 0.4 v cubed, then you will get two variables in your equation, v and t. So you will do separation of variables and you will perform your integration, knowing that at the initial time, velocity is 60 meters per second. So for t equals 0, I know that v0 is 60, okay? And my coordinate is positive downward and v0 is downward. So v0 is plus 60, okay? So now we will write our equations. So as a first step, we write a equals dv by dt. We replace the acceleration by minus 0.4 v cubed, and then we do separation of variables. Since a is function of v, then we will take this function to the side of velocity, and we will take dt to the other side. So we get integral from 60, which is the initial condition of velocity to v, of dv over minus 0.4 v cubed equals to integral between 0 and t dt. Now, how to perform here the integration? Just a general rule, if you have v to the power n, then integration is v to the power n plus 1 over n plus 1, okay? So here, what is the value of n? If I tell you 1 over v cubed, what is n?
-3.
Yes, exactly. So here n is equal to minus 3. Because n is equal to minus 3, then you have v equal to, the integration will be v minus 3 plus 1. So it's v minus 2 over n plus 1, which is minus 2. So the integration will give you 1 over minus 1 over 2v squared. Okay? And already you have a constant, which is minus 1 over 0.4. So in total, when you integrate, you will get 1 over 0.8 times 1 over v squared between 60 and v. So all you have to do is to replace your boundaries, equals to t minus 0, because you are integrating 1. The integral of 1 is t. So between 0 and t, this will give you t. So what you did now is that you got a relation between velocity and time. And here, for example, here, it is good to find the function, not directly replace integration from 0 to 4, because you will need v function of time to find s. This is why I told you in general, I advise you to find the function because you might need it after, okay? So here, to get v function of time, just I multiply by 0.8, and I take 1 over 60 squared to the other side. Then v is equal to this function to the power minus half, because you have 1 over v squared equal to 0.80 plus 1 over 60 squared. So to obtain v, you should do to the power 1 over 2. Okay. So now you got the velocity function, and you will be ready for the next step to get the position function, because you know that v is ds over dt, and already you got v function of time. So you do here also separation of variables. You take dt to the other side, and then your equation will be as follows. So I have v equal ds by dt. I know the function. Doing separation of variables, now I have to integrate both sides. So for position, knowing the boundary conditions that when s equals 0, t equals 0, I will integrate s between 0 and s, and I will integrate time between 0 and t. And here, if you want, you can directly replace t by 4 seconds, because you will not need the function anymore in it. Just now you need s as the final state. So it's up to you. You can find the function then replace, or you can directly do the integral procedure and replace by the boundary equal to 4. And guys, you can do these integrals on your calculators. No need to do them by hand during the exam. Okay, so any integral, a simple calculator can do it. You have the integral function. You just put the function and the bonds of integration. It will give you the result. Okay. So here for the integration procedure, also it's little bit maybe in it. If you call this function u, okay, to integrate this function, you know that when I want to integrate in math, I need, if I have a function u, I need to have u prime with it. Yeah. If I have u prime times u to the power minus half, okay, then I can say that the integration of this function will be u to the power 1 over 2 times 2. Okay, so this is because integration is u to the power n plus 1 over n plus 1. So the integral of this function will be 2 times u to the power 1 over 2. Okay, now you will tell me what is u prime, and do I have it here? Here, if you call this u prime is 0.8. Because it's a constant, okay, since u prime is a constant, you can easily have it appear it in your formula. Because if you multiply by 0.8 and you divide by 0.8, nothing will change, okay? So then you can consider that this is u prime, 0.8 is u prime. I will take it with the function and obtain u prime times u to the power minus half, which integration will give me 2 times u to the power 1 half. Okay, so that's it. But I still have a constant, which is 1 over 0.8. So I divide my result by 0.8. Okay, then I perform my integration between 0 and t, and I can get s as a function of time. Okay, and then I can replace t by 4 to get s, or here I can directly integrate from 0 to 4 because it is the end of the problem, so I will not need the function as function of time. Any question on this?
Doctor, in
Yeah.
this problem, we considered that the projectile directly came in contact with the fluid.
Yes, but it is in direct contact, and they gave you the acceleration function of velocity already, and you don't have to do any physical analysis because A is given function of B, and you have, of course, you have a resistance. Due to the resistance of the fluid, you get this function of acceleration.
Yeah, but I mean, the projectile have a certain amount of time before it came in contact with the fluid.
Sorry, I cannot. It's lagging a little bit. Can you repeat, please?
I'm saying it didn't have some time before it came in contact with the fluid, meaning
No,
it
no.
had.
لا it's يعني الانيشال time it was already in contact. اوكي
Okay.
اللي نحن كبيناها كانت على الووتر على السيرفيس ليفل اوف ووتر.
Okay.
اوكي وهلا بيصير عندك two phases of motion then. إذا أول شيء كانت in air then in water, then you will have two phases of motion. You should study the first phase, and the end of the first phase will be will give you the boundary condition for the beginning of the second phase.
Yeah.
We will do such things in other problems. Okay.
Okay. Thank you.
Welcome. Okay, guys. So I will open a new session because we still have just less than 1 minute. Okay.